Hi everyone, in this video we are going to find a way to actually quantify a transition of energy. So we're going to see if we can figure out how much energy has changed within a given reaction using these beautiful things called bond enthalpies. So let's start off with a standard definition for bond enthalpy. So bond enthalpy, we know that word enthalpy, is strictly the amount of energy required to break a bond. Okay, pretty standard, nothing fancy to that. It's just how much energy is it going to take to actually break that bond, to separate those two atoms. But before I dive any deeper into this, I want to make two different clarifications here. The first thing, anytime we actually break a bond, okay, think about what it is when you have a bond. You're sitting here, here's a carbon, here's a hydrogen, they're holding hands, they have a bond. In order to break that bond, you absolutely have to judo chop it, like whoosh, hit it as hard as you can. You need to supply it with energy. It's not just going to magically break, you need to hit it, give it a force that's going to cause that to separate. So when you think about breaking a bond, you think about the fact that it needs energy. It requires energy. And so if something requires energy, that's an endothermic process, meaning that our delta H value is actually going to be positive. So the opposite of which would be making a bond. So make a bond. So this is the opposite. It's not going to require energy. It's actually going to release energy. And so the way you can think about this is that if you have a carbon here and a hydrogen here, the entire driving force of chemistry or science is to always get to a place of lower energy. So if you are trying to make a connection between these two things, trying to force them to create a bond, the only way that's going to happen is if they start here at a certain energy and they relatively drop, if they get to lower energy. And so the only way you can do that by making a bond is releasing energy. So by releasing energy, we know that this would be an exothermic process, so our delta H value has to be negative. Okay, so now what we're going to do, let me just sum this up because that's a lot of things I just said, is we're going to try to use these things called bond enthalpies, which is the amount of energy required to actually break that bond. We're going to use these values to try to calculate what's going on with the total energy flow that's happening for our entire reaction. So let's start off with the simplest version of a combustion reaction that we know of. And so that would be to take two hydrogens, treat it with an oxygen, and then create two water molecules. All right, so now what I'm going to do is point out this two right here. Do not forget that we're creating two waters. At the very, very end of the video, that's going to come racing back, so just keep that in the back of your head, okay? So now what we're going to do here is we're going to draw this out. So we know that we have two hydrogen molecules. You have to draw two. You can't draw one, you have to draw two. We also know we treat that with oxygen gas, so oxygen's a diatomic molecule, and then we create two water molecules. So here's one water molecule, and here's a second water molecule. All right, so now we've written out our chemical equation, we've drawn this out. Now what we're going to do is actually try to quantify this, put numbers to it. And so the way we do that is by solving for something called delta H of our reaction, so that's the total enthalpy change of our entire reaction, so the entire combustion of hydrogen gas. And so what it ends up being is something called bonds broken minus bonds formed. Okay, so let's talk through that. In order to create two water molecules, I need to create four oxygen-hydrogen bonds. Hopefully you see that. 1, 2, 3, and 4. I have to create all four of those in order to actually make water, right? But in order to do that, if we're starting with hydrogen, hydrogen, and oxygen, oxygen, I absolutely have to break all of those bonds. So in order to calculate the total energy transition or total energy flow of your reaction, you break all the bonds on your reactant side and you make all your bonds on your product side. So before we actually put numbers to this, I want to ask you a question. So would you expect our delta H of our reaction to be positive or negative? I promise you, you can do this question, but you just have to think about it. All right, positive or negative? Go. All right, did you get an answer? Hopefully you did, and the big hint was that I used the word combustion. If I ever use the word combustion, you immediately know that we're releasing energy, okay? So combustion means, let's write this all out just in case you weren't there. Combustion means releasing energy. If you're releasing energy, then that has to be an exothermic transition. If you're releasing energy, it's an exothermic transition. That means that your delta H has to be negative. So the correct answer to this question was absolutely negative. All right, so now we know what our answer should be, but now instead of just saying negative some value, let's actually put a number to it. And what we need to use are these things called our bond energies or our bond enthalpies. So just like I said before, this is the amount of energy required to actually break that bond. So in order to read this chart, what you need to do is go all the way here to your left side and pick something. So let's say we want to look at a hydrogen-hydrogen bond. So you're going to find the hydrogen on one spot here, the hydrogen on another spot here, and then the value where you bring these two together, so literally just bring your fingers together, that's going to be the value for that type of bond. So if we look at this properly, we would see that a hydrogen-hydrogen bond actually has a value of about 436 kilojoules of energy per mole. So let's actually do this for our problem, all right? So we're solving for delta H of our reaction. I'm going to rewrite this for you so that we don't forget. But basically what we said is that we needed to do our bonds broken, so that was 2 of our hydrogens, okay? So 2 H bonds. Okay, we also had to break apart an oxygen double-double bond. Those are bonds broken, minus our bonds formed. And we said we created 4 OH bonds. All right, so now I want to go back up here and make sure you're with me on that. So let's go back up to our drawing here. So we're saying that we are going to break 2 hydrogen-hydrogen bonds. We're going to break 1 oxygen double-double bond. And then we're going to create 1, 2, 3, 4 oxygen-hydrogen bonds. So hopefully you're with me on that. If you're not, just stop for a second, go back and draw it out. So that's our formula. This is what we're trying to plug values into. So again, we said that we have our delta H of a reaction is equal to, we are breaking 2 hydrogen-hydrogen bonds. So let's go to our chart. Hydrogen-hydrogen, if we put those together, we end up with 436 kilojoules per mole, plus an oxygen-oxygen double bond. So now what we have to do is go down here to the bottom where we're talking about double bonds, and right here you can see that our oxygen-oxygen double bond actually has a value of 498 kilojoules per mole. So hopefully you can see that it's very important. Up here at the top, these are single bonds only. Bottom here is going to be your double bonds or even your triple bonds. So make sure you're looking at the right chart. All right, so those are all of our bonds broken. Now we need to add our bonds formed. So subtracting out 4 times an oxygen-hydrogen bond. So what I like to do is go up here to the top because this is where your hydrogen is. Come all the way down here to oxygen and come right here. You can see that an oxygen-hydrogen bond is about 463 kilojoules of energy per mole. Now you have all your numbers. All you have to do is plug that into a calculator. So if you do that properly, you end up with a delta H reaction. So you have 2 times 436 plus 498. All of that's one number. Subtract that from one number, 4 times 463. If you do that properly, you get a delta H reaction equal to negative 482 kilojoules of energy per mole. Now, before you do anything, always stop and say, is that the right number? Because for our example, it absolutely is not the right answer. Because what we did here is we solved for 2 moles of water. But if you go to our unit, this is saying kilojoules per 1 mole of water, per mole. So what we have to do, and this is the part that everybody always messes up, so please, like star your notes, do whatever you have to do. This is the part where people mess this up. So this is the number actually for 2 waters. Okay, but we want to know for 1 water. So all we do is we take our delta H of a reaction, which is equal to negative 482 kilojoules. We have to divide that by 2, and now we have our true answer. And so let me get that. That is actually negative 241 kilojoules of energy per mole. And that number makes total sense. Okay, it's negative. We predicted it would be negative, definitely exothermic, and we have this value here. All right, so I'm going to leave you with one more here. I'm going to let you actually do this one on your own. Okay, so here's the problem I want you to solve for. CH4 plus 2O2 going to CO2 plus 2H2O. So I balance that for you. You don't have to do that. What I want you to do is solve for your delta H of your reaction. Okay, so solve for that number. You're going to have to use this table here. So I'm going to leave this here so that you can write your reaction, but please go back into the video and make sure you use these values right here. These are the ones I want you to use when you're calculating it out, okay? All right, so go ahead and solve this out. I'll meet you back here in just a minute. Go. All right, did you get an answer? Hopefully you did. This was definitely a tricky one, so please do not panic or get frustrated if you weren't able to solve this. So let's work through this together. The very first thing you do is draw everything out. So methane looks kind of like this. Okay, we only have one. That's fine. Then we have 2 oxygen molecules. Then those are our bonds broken, okay? Then we create 1 carbon dioxide molecule and 2 waters, all right? So it's just a little bit more complicated than what we did in the previous problem. All right, so it's a lot more complicated. All right, so what we do now is write out our equation. So delta H of our reaction is equal to bonds broken minus bonds formed. So the first thing we do here is start with our methane. I see that I have 1, 2, 3, and 4 CH bonds. So 4 CH bonds plus 1, 2 oxygen-oxygen double bonds. So we're going to multiply that times 2. Those are all the bonds that we have to break. So I circled those, but please remember we're breaking every single one of those in order to create our bonds on the other side. So bonds broken minus bonds formed. Let's start here. I see 1, 2 carbon-oxygen double bonds. So we have 2 CO plus 1, 2, 3, and 4 oxygen hydrogen bonds, okay? So that's our formula. Now hopefully what you're able to do is go back to that chart that I have previously on earlier slides and actually find all these values. So I'm just going to plug these in. Hopefully you're able to get these. So for carbon hydrogen I have 413. For my oxygen-oxygen double bond, I have 498. We already used that value, so hopefully you didn't even have to look that one up. For our carbon-oxygen double bond, I found a value of 799, plus 4 times our oxygen-hydrogen bond, which is a number we already used, which was our 463. All right, so now all you have to do is plug this into your calculator, and if you do that properly, you end up with something like negative 802 kilojoules per mole. Now, this is tricky. This is one of the biggest questions I get. Well, they go, all right, Dr. B, I don't understand because now I have 2 waters, 1 carbon dioxide, and it's not per 1. Do I divide by 3? What do I divide by? Nothing. You don't divide by anything. If you're creating multiple products, what you do is you just report this number and you say per mole of reaction. All right, so you add that word reaction in there. Now you've covered all your bases. You can say for as written, so 1 methane, 2 oxygens, 1 carbon dioxide, 2 waters, it is required that we take negative 802 kilojoules per mole of a reaction in order to have this reaction pursue, okay? So hopefully you can check this. You can see that A, it's exothermic, B, it's negative, so you know everything makes sense. Hopefully this is all clicking for you. If not, please stop. This takes so much practice, and you need to get very, very, very comfortable with this chart. If you were not able to pull the data off that was necessary, you need to go back, start asking questions, talk to your peers, and figure it out, okay? Have a great week. Take care of yourself, and drink water.